Qualitative analysis is what? Silly? I'm sorry?
When we study different ions.
Well, it's not really, I mean, the goal of qualitative analysis is not just to study them, but to do what? Yeah, identify what ions are present. And so if you get a positive test result, what that means is that you confirm the presence of the anion. If you get a negative test result, what does that mean? It means two things. One, it could be that you don't have any, or two, it could be that it's present but below the detection limit of the test. These tests don't all have the same sensitivity. Some tests are like hypersensitive. For example, sodium test is so hypersensitive that contaminating your sample or contaminating the test is a real big problem. And so people get false positive test results for sodium just because of contamination, not because they had it in their unknown. Whereas other tests are not very sensitive and hard to detect sometimes. For example, the calcium flame test is hard. You know, normally the more you have, the better. Most tests, I would say, are not so easy to detect sometimes, and so you have to be careful. The only one that really is too sensitive is the sodium test, which gives a lot of people problems. And so what are the tests that you'll be running? What have you guys prepared? All right, so the first test that you did was prepared is the sodium test. All right, the sodium test is very difficult because of the contamination issue. Now, we don't know, what. So there should be nothing on this. This is just a strip of wire. It's either platinum or some other high melting alloy. Wow. All right, do you see this flame color? That's a positive test for sodium. And actually do this in the hood, because other people, they dip it in their unknown and then test it, but your unknown can contain heavy metal ions and other poisonous ions. And so you want to do this in the hood so any vaporized metals aren't inhaled. But this is just sodium. But that's a positive test for sodium. The problem is sodium's everywhere. So for example, this is very hot right now and I wouldn't want to touch it, but if you touch the wire with your fingers, you leave enough sodium residue to give a very strong positive test signal. When you're working with very, very small concentrations of sodium, you can't even use glass. If you use glass contains sodium ions, most glasses do. Those sodium ions will leach out into the water. If they leach out into the water, then you're going to get a positive test. So when I was doing sodium analysis for a while, everything had to be stored in polyethylene. Polyethylene wouldn't leach out sodium ions. So it was a pain, and not only that, everything you had to be exceptionally careful with, because almost everything seemed to leave a residue of sodium ions. So it really screwed up the analysis results. And so what do you do? This is so strong you can easily see it right here, right? And that means the first thing you have to do is clean the wire. But how long does it take? Because it's very minute amounts of sodium ion will give a strong color like that. How long do you have to clean the wire? People are cleaning the wire for like 30 minutes. They're trying to burn off all that sodium residue. After 30 minutes, it's still not burnt off. They give up and they go ahead with the test and get a false positive. But what you have to do is you have to burn off this residue completely. Now there are some tricks to burning off the residue completely. Some of the tricks would be to dip this in concentrated hydrochloric acid. You dip it in concentrated hydrochloric acid and burn, dip it and burn or vaporize it off. You do this in the hood because concentrated hydrochloric acid is very strong fumes. That helps speed it up. Other things people do is they fuse other salts like calcium, like maybe calcium carbonate or something. They'll melt it onto the end here and then burn it off that way. Hopefully it takes it off. So they get it really hot, put it in salt, melt it on there, burn it off. But we'll be doing the HCl. When we do the HCl, the issue is with the glass here. You can tell what kind of glass you have by looking through the tube like this. You know, whether you have quartz glass or Pyrex glass. Quartz glass is higher purity. Quartz glass shouldn't have any sodium ions in it. Quartz glass is also much more expensive. If you look through the tube this way, if you see a green color means you have Pyrex glass. Pyrex glass, little lower temperature. I can't. It does okay with thermal shock, but quartz glass is a little better for heat. But this is, I'm pretty sure these are in Pyrex. This looks like Pyrex here. This is Pyrex. And so be careful. When you heat up the glass and you put it in water, it will result in thermal shock and shatter the glass. Or the other thing is a process called devitrification, where the glass crystallizes rather than stays a glass. Glasses are amorphous, as solids, but they can crystallize. All right, so you know, the best thing to do with this is just to clean it once, right? Because the cleaning process takes so much time, and therefore I would postpone the sodium analysis until you do the calcium, because calcium is very difficult to see. If you have just a trace of sodium in there, it'll completely drown out calcium's color. You won't be able to detect it at all. And so what you're going to do is you want to get this so clean it imparts no color to the flame. And then what you want to do is you want to test for your calcium when you get there. It's much later in the procedure. You want to test for your calcium, which gives a brick red color first. Okay, after you test it for calcium, then test for sodium, because once you test for sodium, you're going to be there for 30 minutes trying to clean it. Okay. All right. But anyway, what are we doing in the sodium test? What we're doing in the sodium test is this. In sodium ion test. So these are going to be written in this form. We're going to have an observation and then an equation associated with that observation. And so the observation is the unknown AQ. You're going to have aqueous unknowns, not solid or whatever. The unknown AQ is going to be put into a flame. And then what we're going to see is a yellow-orange color. A yellow-orange flame means this is a positive for sodium ion in your original unknown. So we could say this is going to be for a positive test. And basically, if we have sodium ions present and we put those in the flame, what's going to happen? What's going to happen is the sodium ions are going to vaporize into a gaseous state. Now, do you know what a flame is? Like a methane oxygen flame? You know, when you look at like a blue flame like this, I think I asked you this before, but is that blue color from the water that's being formed in the combustion? You know, water is blue, right? Or is it blue or colorless? What is water? Water is, colorless, supposed to be colorless. Unless it's a deep body of water, I'd say. But anyway, what is in this flame? Do you see the cone? What does a cone represent? The cone represents different regions of the flame. Like, for example, inside the cone, it's non-stoichiometric. It's excess gas, right? And so inside the flame, if we have excess gas, we call it the reducing part of the flame. So at the cone, on the surface of the cone is stoichiometric. We call it stoichiometric part. And on the outside of that is the oxidizing kind of part. And so there are different regions of this, and the reducing parts and oxidizing parts of the flame. The hottest part is where we're going to get the most heat production is going to be at the base. No, but on the surface of the cone is going to be the hottest part, right? Right on the surface, because that's where stoichiometric. Well, anyway, in this flame, the sodium ions can get reduced because a flame is what we call plasma, and the plasma has free electrons, that get knocked off of atoms and other species, molecules, whatever. And so what can happen is the sodium ions can get reduced to sodium metal inside the flame itself by picking up an electron. And so it picks up an electron, and let's do this. It just forms gaseous sodium atoms. And the gaseous sodium atoms, plasmas are known as high. When you heat up a gas, you keep heating it and you keep heating it, eventually the gas turns into plasma. And plasmas are super hot gases. These super hot gases have violent collisions which knock electrons off atoms and other species. And so we got ions in there, and we got violent collisions, and we got electrons in there. And so some of these are going to result in this, but sodium's going to undergo a collision. As sodium undergoes a collision, electrons get promoted to a higher energy orbital. And this is showing an excited sodium atom, and that doesn't stay in the excited state forever. Eventually it's going to drop back down to its ground state. When it drops back down to its ground state, it emits an H nu. What's an H nu called? H nu.
Is that a radical electron?
Hmm? I'm sorry?
Is that a radical electron?
No, H nu is not a radical electron. H nu? It is energy, but what is it called? H nu. So if I have a mole of sodium, so it would release a mole of H nus, which are called photons. Yeah, H nus are photons, right? This is a photon. This is common the way people call photons, right? H nus, or HC over lambda. A photon is the characteristic spectrum. And so this is the test for sodium, and I recommend you not doing the sodium just yet. I recommend holding off on the sodium for a while. All right, what's the next test? So if you get that yellow-orange flame, it could mean that, well, you have it and you're unknown, or you just contaminated and got a false positive. You got to be very careful.
What are we storing our unmet solution in? We're storing it in glass?
You're storing it in glass, but you don't have to worry because the detection limit, the levels I'm talking about are like barely detectable. You wouldn't be able to detect the amounts that I'm talking about using qualitative analysis. The amounts that I was talking about are just trace amounts. So, this was extreme, the stuff. What I was trying to do is determine how many sodium ions were in this polymer. And the polymer didn't have very many sodium ions and didn't have much polymer. And so it had to be extremely careful. In fact, this is what UCLA. UCLA, I used to take a big polyethylene carboy, and I'd have to take it to psychology. Because in the psychology building, that's where the distillation apparatus was kept. Don't ask me why, but they kept it in psychology. And so I think physics would use it, engineering would use it, chemistry would use it. It's special water, very expensive water. And so it's not just a regular DI like this. And so I do that. Everything was like that, you know, an extra pain to deal with. So a lot of work. And so we use very expensive water and all polyethylene beakers, polyethylene everything, you know. And, it's a lot of work. There, I still did 3 trials, so and, still a lot. All right, let's go on to the next ion, which is ammonium. All right, what does the positive test for ammonium look like? And so look at our observations. Our observations are going to be like this. We take an unknown aqueous. This would be a fresh sample, you know, unknown aqueous, or it could be the same sample as your sodium test because that shouldn't have ruined the ammonium. We don't need much here, but the more you have, the easier it is to detect, but the more you use, the less you'll have for other tests. So there's a trade-off here between using too much, too little. And so the unknown aqueous, we add some sodium hydroxide solution to this. This is just for the hydroxide. This is an acid-base reaction. What we're going to get is we're just going to get a CCS, right? And then what we're going to do with this CCS is we're going to heat it under litmus paper, under wet litmus paper. And so in here, we're going to have our ammonium, and then it's going to be just plus hydroxide, which is going to give us ammonia AQ plus H2O liquid. Uh-huh. Okay, CCS. It might not be a CCS, now that I think about it, because you could have other stuff. Or you know, you might get precipitates, etc. But does somebody know what CCS stands for? Clear colorless solution. So this CCS is common. Clear colorless solution. It would be a clear colorless solution if the only thing you had in there was like ammonium chloride. But if you had other things like iron, if you had iron there, you're going to get brown precipitates or green precipitates. You know, nickel, you get green precipitates. You know, so you could have other things. You know, or precipitates. These precipitates and color changes can tell you about what other ions are present. Clues that tell you, that might tell you what other ions. Present. All right, when we heat this up, what's going to do is it's going to take the ammonia that's dissolved and form NH3 gas. And just drive it off as a gas. This NH3 gas will rise up, you know, as gases do. But there's something special about NH3 gas. NH3 gas, well, NH3 has, what are the chemical properties of NH3? It's a base. CO2 is a acid. O2 is neutral. In terms of acid-base properties, if we're going ammonia gas is base, CO2 gas is acid. A lot of people wrote it wrong. A lot of people said stronger acid like H2SO4 to weaker acid, water. Water is not the weaker acid. This is why I try to get away from formation of water. Water wasn't actually formed in the quiz number 1, calcium carbonate with sulfuric acid. It goes from stronger acid, sulfuric acid, to weaker acid, CO2. CO2 is the weaker acid, not water. That's a little side note. But, you know, we can tell O2 is neutral, N2 is neutral, you know. And so if we have a basic gas, what other basic gases do you know? Gases that are bases. Well, amines, but there aren't too many amines. You'd notice it. And so what happens is this. How do we test for base? You know, how do you test for base? A litmus test. So this is how we're testing, right? We're going to just put a watch glass here. And then we're going to stick a piece of litmus paper on the underside of this watch glass. How do you get the litmus paper to adhere to the underside of a watch glass? Yeah, moisten, right, exactly. Moisten litmus paper right here. So we'll just attach a piece of litmus. But, you know, this litmus should only be exposed to the gas because the solution has what in it? Sodium hydroxide. You know, if this solution is very basic. And so we just want the gas to come in contact with the litmus, not the solution. And so we let the gas rise up from the surface of the solution, and gradually it's going to change. Well, what color do we use for testing bases? Red litmus or blue litmus? Red. And so what happens is red litmus turns blue. Upon exposure to the gas. And so what are the equations here? Well, I wrote one of the equations over there, but let's rewrite it here. The equations for these reactions, you know, if we have ammonium ion present, then the hydroxides attack that to form ammonia, A cubed plus H2O liquid. When we heat that, that dries off the ammonia as a gas. Erase this. Then the ammonia gas can come into contact with litmus. Litmus is, you know, can be written HLIT. You know, litmus is a organic acid in red form. In red form, it's an organic acid, except the anion for this is kind of complicated, so we'll just use the abbreviation LIT for the anion. And so it's an acid, and what do acids do? Well, this is red. They undergo a Bronsted acid-base reaction will undergo proton transfer. So on the litmus paper itself, the ammonia will be neutralized by the litmus, form ammonium. Technically, it's not totally neutral. You know, it's not H7 because ammonium is actually an acid. But anyway, it'll do this, and then we'll end up with the litmus anion here. The litmus anion is blue. And so this is organic acid that, interestingly, its conjugates have different colors. The conjugates here, the acid form is red, and the base form is blue. It's like phenolphthalein. Phenolphthalein is an acid. In acid form, it's colorless. In base form, it's pink. And so it just changes the electronic environment. When you lose that proton, you know, the orbitals, whatever, you know, the electronic environment changes and the orbital energy levels change. And this kind of stuff happens. Okay. So that's what we have. Any questions on this? This doesn't take very much time, right? You don't want to use all your samples. You only have a limited amount of unknown sample. And so some people dump their entire unknown sample in here, and then they can't move on from here. They ran out of unknown. And so you have to think about how much you want to use for this particular test. Okay, what's next? Silver ion test. Okay, now these, the sodium test and the ammonium test can be done at any time, but the next series has to be done in sequence, because the next series of tests relies on separations and isolations. Right? To isolate and separate over a long sequence like this is difficult. So sometimes by the end, by the time they get to step 20 or something, they've lost so much of their unknown ion they can't detect anything. They get to step 20 and they're expecting a precipitate and nothing happens. It could be different reasons, but one of the reasons could be because their separation and isolation techniques weren't very good. And so when we want to separate and isolate things, we want to make sure we capture as much of it as possible. And so this is an experiment that's best it's best that you don't cookbook it. Do you know what I mean by cookbook it? You don't follow the procedure exactly as written. If you follow the procedure exactly as written, you're going to get poor results, guaranteed. Why? Because you think if you follow the procedure as written, you're doing good. No, you're not really doing good, because this procedure is written for any old unknown, right? And if it's written for any old unknown, then it's not written specifically for your unknown. And so there are some rough approximations about what kinds of volumes are required for any old unknown, right? And sometimes those approximated values that they use, or volumes or amounts that they use, aren't so good, aren't so close to what you actually need. And so this is why we need to understand the reactions that are happening and what we're trying to achieve in particular steps. And so a lot of people, what they do is they leave this procedure in flowchart form. If you leave it in flowchart form, you just need to add a few details. Like, for example, in the flowchart, it might say HCl. You might, add some details. About 3 drops or something like that. Or the concentration, 6 molar, about 3 drops. So you'd have to add a few details into the flowchart itself. But you can leave it in flowchart form. That way you get a better idea of what you're supposed to do, because a lot of people get caught up. Oh, I'm in step 6E, but they have no idea where they are at. They just know they're on step 6E, wherever the heck that is, in some big, complex of procedure, lost in some maze, no idea where they're going, right? And so if you have the flowchart, or just make a flowchart, make a copy of the flowchart, have it handy. If you have a copy of the flowchart handy, you can always see where you're at and what you're trying to do at that particular step. And so we're going to have how many potential ions in here? We're going to have 10 ions, right? 10 ions. Cations. Possible. Okay, so maybe I'm going to use some kind of code here. So this dashed line means it's an aqueous solution. So I have 10 cations possible. What are those cations? Silver. What else do you have in there? Ammonium, sodium. Yeah, the list is there, right? But that's a big mixture. And so how do we separate the ions? We separate the ions by taking advantage of their chemical properties. One of the biggest chemical properties we're going to take advantage of is solubilities. But there are other chemical properties that we can take advantage of as well. Redox properties, acid-base properties, Lewis acid-base properties, a whole slew of others. We're going to use a lot of chemical properties to separate ions from each other. And so what's the first step in the separation here? Precipitation of silver using what?
Hydrochloric acid.
Yeah, hydrochloric acid. Now, with chlorides, what will precipitate? What cations will precipitate with chloride? Silver, lead, mercury. Silver, lead 2, mercury 1. Well, do we have any lead 2 in this? No. Do we have any mercury 1? No. And so this is the easy version of qualitative analysis. We used to do the hard version of qualitative analysis years ago, where you would have mercury and lead present as well. And so since we don't have any, we have to qualify this. There's no lead and mercury present in that mixture. If there's no lead and mercury present, then the only thing that's going to precipitate out with HCl is silver. And so you should get a precipitate of silver chloride solid. Okay, how many drops and what molarity of HCl are you going to add? How many? 2 drops of 6 molar HCl? Okay, right there, I see a problem. 2 drops. Well, do they know how much silver you have present in your unknown? What if you have a lot of silver present in your unknown? If you have a lot of silver, it might take more than 2 drops. But if you only use 2 drops, what's going to happen to all that unprecipitated silver? It's going to stay in solution. If you add 2 drops and 2 drops was not enough, then what you're going to end up with is silver making it over here with the other ions. If silver makes it over here with the other ions, it screws up all these tests because now you have silver in there, which alters the color, alters what happens at each step, screws everything up. And so this is why I say, the good students don't follow the procedure as written. The good students modify the procedure to do what they want it to do. And so how much HCl should you add then? If you're a good student, how much HCl should you add? Until there's no more precipitate. And then stop. Well, how do you know if there's no more precipitate? Because it gets so cloudy, It's all cloudy and white. You add a drop, you can't see anything. It's like being in a dense fog, Is it getting foggier or not? It's hard to tell because it's already so foggy you can't see anything, right? And so how do you know? Okay, you're right. We're going to centrifuge it. And so what we do is we add until it gets too cloudy, we can't see anything. And then we're going to use one of these centrifuges over here. My one's broken. The centrifuges have different inserts depending on what size test tube you use. Alright, so there's a lid on here, and then to turn on the centrifuge, you just turn this dial, there's a timer. Then it'll start to spin here. Listen to the centrifuge. Do you hear it? When it's reached the maximum RPM, that's enough. usually. So you just let it reach maximum RPM and then you just rotate the dial to turn it off. But it's still spinning very fast. These centrifuges you can break with a paper towel or something. And so you just put it on the black ring on the top. But you don't want to break it to a sudden stop, because if you break it to a sudden stop, it could dislodge the pellet on the bottom of the test tubes. You'd have to recentrifuge it. These are the inserts in here. This one's for a smaller test tube. I'm going to take out the insert so I can use a bigger test tube. When I put a test tube in here, I have to make sure it's you hear that? Doesn't sound good, right? Why? It sounds actually awful and vibrating too much. It's unbalanced. That's an unbalanced centrifuge. In order to balance it, if you're trying to centrifuge a cloudy solution here, you have to make a counterweight. And so you just get another test tube and fill it approximately the same height, and then it should be balanced. Does that make sense? All right, if you centrifuge it, then you can quickly get a cloudy precipitate to settle at the bottom of the test tube, and then just add 1 drop of HCl here and watch it as it travels down. You'll see some turbidity as it travels down. Make sure it doesn't form any more cloudy white suspension. If it does, what should you do? Keep adding more. Right? You have to be careful, because you might say, well, I want to be safe, so I'm just going to add a large excess. But if you add a large excess, you have 2 problems. 1, you have to clean it, right? And 2, a large excess could result in losing precipitate. And so two problems: the contamination and losing precipitate by forming complexes. And so, let me show you what I mean by that. A lot of the reagents that we're going to use are in these little dropper bottles here. And these dropper bottles should be in alphabetical order, in numerical order. So I was going to show something with lead. Lead is an extreme example. When you try to precipitate it out with hydroxide, you'll maximize. What happens is you get a lot of precipitate, and then you keep adding hydroxide, and the precipitate disappears. Disappears by adding too much precipitating agent. Normally, we want to add an excess of precipitating agent, and here we should add a small excess, but not too large of an excess, because what can happen are these kind of complexes, like dichloroargentate, one can form, which would redissolve the precipitate. It's not a huge problem. For lead, it is, kind of a problem. So we don't have any lead, so we don't have to worry about it. All right. The white precipitate's not enough, because if there are some additional tests we can do, then we can have additional confidence in this. So so if we get a white precipitate here, that's good. But what we're going to do is, there might be lead, or there might be mercury, but lead chloride and mercury chloride are going to have different chemical properties than silver chloride. One of the chemical properties of silver chloride is silver ions love to form the diamine silver ion complex. And so here what we're going to add is ammonia. Now we're going to add it to the solid itself. So now this is very important here, and that is, there's a lot that goes into this particular separation here. One, how much HCl do we add? Yeah, enough to precipitate all of it. 2, how do we separate the solid from the solution? Okay, now we've added enough HCl. What we're going to do is we're going to do a final centrifuge, right? And then we're going to separate the solid from the solution, but can you remove all the solution? No, so what we're going to do is we're going to remove as much as we can by decanting it. But sometimes decanting it is not enough. So sometimes what we'll do is we'll get a pipette and suck the solution off the top of the precipitate pellet. But still there's a little bit of residual solution left there, right? As you can't, it's not like a vacuum. You can't vacuum all the crystals, get rid of all that solution. And so begins. This is the common technique that we're going to do. The common technique that we're going to do is we are going to wash this multiple times. The first wash of the crystals here, so we wash it, stir it up, centrifuge. The first wash is going to be contaminated with this. So should we discard that? No, we don't discard the wash. The first wash we never discard. The first wash should be combined with this, otherwise we're losing some ions, right? What about the second or the third wash? I don't know. Does it say to combine the second wash? Add washings to this? If we combine the second wash, okay. You know, if we combine the third wash, maybe not okay, because the other problem we run into is over dilution. You know, if we over dilute it, it's hard to detect. You know, the more concentrated it is, the easier to detect. The more diluted, the harder to detect. And so maybe the third washing we'll just throw in the waste, because that shouldn't contain much. You know, primarily the first washing is going to be the most dirtiest, the most concentrated in the other ions, which you want to save. You want to save all those ions. Is that clear? If you don't wash this, then this is going to look ugly. When you add the ammonia to this, you're going to get all kinds of precipitates. Hydroxide precipitates, right? But if we add ammonia to this now, this is what should happen. We should get a CCS. The CCS is going to consist of the two ions, diamine, silver ion, and chloride. Now I'm going to get rid of these brackets here. And so the reactions that are happening here, or the equations that are happening, silver plus chloride, you know, well, I'll just do that later. So how much ammonia do we add? How many drops does it say to add?
4 drops.
4 drops. That's ridiculous. A lot of people do 4 drops. A lot of people do 4 drops and they don't even dissolve all their silver chloride. Is that good? No. And some people do 4 drops and it's dissolved in the first drop. That's bad too, because there's too much excess ammonia. Excess ammonia will give you trouble. And so what we do is we add a drop. You don't just go boom, 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 4 drops. And the same thing with the precipitation. You know, we add 1 drop. See what happens. 2 drop. The same thing with this. When you're adding the ammonia, you add 1 drop. If it dissolves in 1 drop, you add the remaining 3. No. If you add the remaining 3, you're going to screw up your experiment. If you add 4 drops and it still hasn't dissolved, should you add a 5th drop? Yes, definitely. A 7th drop, an 8th drop, a 9th drop, 10th drop? Yes. You got to add the minimum amount required to dissolve all your silver chloride, because it should form the CCS here, their colorless solution. If we've done this with a minimum of ammonia, then what we're going to do is we're going to kill it off using some nitric acid. We kill it off using nitric acid, and we're going to reprecipitate out our silver chloride. That. And so this is the test for silver ion. terms of observations and equations that we should be able to see. And so if we get a positive for silver ions, then what we have is our initial observation, we'll call it observation 1, is our unknown aqueous plus HCl yields a white PPT. That PPT is, we look at the equation for one. That PPT is because silver ions, like chloride ions, this is just a metathesis reaction, or silver chloride's solid. All right, 2. So look at the observation here. We're going to take the PPT from 1 and then add ammonia to that. Add ammonia, and the PPT should dissolve into a CCS. The equation for that is this: silver chloride solid plus 2 ammonias yields this: diamine, silver ion, and chloride in solution. What kind of reaction is that? When we form complexes, what kind of reaction is it? Formation of complexes is what type of reaction? Well, maybe I shouldn't wait so long for the quiz, because the longer I wait, the more stuff is forgotten, right? Or maybe you didn't catch it. What kind of reaction is it? Electron pair donor, ligand. Ligands are also known, aka as Lewis bases. What kind of reaction is it? Lewis acid-base reaction. So this is Lewis acid-base reaction. Okay, 3. Then what we're going to do is we're going to kill it off with nitric acid. And so the different ways we can do this. We can do this by Le Chatelier's principle. Le Chatelier's principle says we're going to have some kind of equilibrium between silver chloride and 2 ammonias, which can be represented like this. If I add more ammonia, it shifts it to the right? But what if I decrease the amount of ammonia? If I decrease the amount of ammonia, it should shift it to the left in favor of precipitation. And so how can I decrease the amount of ammonia? Easy. Ammonia, what's one of the chemical properties of ammonia? It's a base, so if I add acid, I'll kill it. And so I'm going to add acid to this. I need nitric acid in particular because nitrates are unreactive in metathesis. And so if I add that, I'll add 2 H pluses. It's going to convert the 2 ammonias into 2 ammoniums. And so in other words, I'm going to decrease the ammonia by forming ammonium. And then it should shift it left, right? And I should do what? I should reprecipitate out my silver chloride. This is Le Chatelier's principle in action. So we're doing a Le Chatelier's experiment, but you're already doing one in this lab. This is Le Chatelier's experiment. Sometimes people add so much ammonia that when they try to kill it off using nitric acid, they have to switch from test tube to beaker. And still it doesn't work because now it's way too over diluted. And so a lot of people fail this test. It's because of the amounts usually. They aren't paying attention to the amounts, which can cause trouble. Okay. What's next?
Separation of iron from
All right. Which one of those 3 is next? Iron? Iron's next? All right. One of the other ions over here should be iron 3. And so if we had iron 3 here, it should filter all the way over here. And so what we're going to do is we save this solution. We got to save this solution because that's where the other ions are going to be for subsequent testing. And so we have to follow the sequence in order for this to work. Otherwise, we get the wrong mixture of ions, which gives us results that are difficult to interpret. And so for the positive test for iron 3 in solution, it's going to look like this. You know, the first step is we take the unknown and then add HCl. And for iron 3, we should get, does chloride react with iron 3? No, does H plus react with iron 3? We should get no reaction here. And that is iron 3 plus, chloride yields Nr. No precipitate there. That's important because that's the first step in our analysis. That's how we separate the iron from the silver. If the iron also reacted with the chloride, then we might not be able to separate it from the silver, right? So this is our observation, we call it. This is our equation here. All right, what's next? What do we do to the solution? We add 2 drops of ammonium chloride, and then what? Huh?
6 molar ammonia.
Then 6 molar ammonium. And so what we're going to do is we're going to take our iron 3 and add this. It's ammonium. A mixture. This kind of mixture is a buffered mixture. Tell me, what does iron 3, aluminum, and chromium share in common? They're charged. Let me do an aside here. We do hydroxide precipitating agents. One, straight hydroxide, like sodium hydroxide, etc. This is what we call full strength, or what I call full strength. I don't know if anybody else calls it full strength, but that's full strength, right? So if you had 1 molar sodium hydroxide, how much hydroxide would you have? One molar, right? That's a strong electrolyte. 1 molar. If we add ammonia, if I had 1 molar ammonia, am I going to get 1 molar hydroxide? Am I? If I had 1 molar ammonia, no, I get a tiny bit of hydroxide due to the hydrolysis of water. The hydrolysis is not very favorable, right? And so we're going to form a little bit of ammonium and a little bit of hydroxide. And so this is a reduced strength, right? Reduced strength because we are not going to have as much OH minus. We can further reduce that strength by taking advantage of Le Chatelier's principle. Plus ammonium we call buffer. What happens if I add ammonium to this? So now I have ammonia in water, and it hydrolyzes water to form a little bit of ammonium and hydroxide. What happens if I take this equilibrium and add ammonium to this equilibrium? It's going to shift it left. And so by increasing the ammonium concentration, I'm going to shift to the left, further reducing the hydroxide. And so this is the weakest. And it depends on how much ammonium you add. The more ammonium you add, the weaker it is in terms of hydroxide concentration. Weakest. We need this weakest one to prevent precipitation of the 2+ cations. What are the 2+ cations?
Sodium, magnesium,
Well,
magnesium.
like magnesium, we don't want to precipitate out magnesium hydroxide. And so to prevent precipitation, we keep the hydroxide concentration so low it doesn't precipitate. Magnesium requires more hydroxide because it is more soluble. Why would the 2+ be more soluble than the 3+? You should try to make yourself more comfortable speaking in the jargon. Why would the 2+ cations be more soluble than the 3+ cations? You looked at the solubility rules. What's the pattern on the solubility rules? How do you learn this stuff? How I learned this stuff is by repetition. It's over and over again. This is why I kept rereading my notes. So it's like a drill. You drill it into your memory. Pretty soon I'm not going to do as much repetition because I just got to get back on schedule. I've been doing a lot of repetition just to drill over and over again, but I'm going to start skipping that repetition and just moving on. But you should make an effort to do it. Just because I'm not going to do it because I'm running out of time doesn't mean you don't have to do it. You should do it too. And so make sure. But it has to do with Coulomb's law, right? Electrostatic attractions. Higher the charge, the greater the electrostatic attraction. And we see that with lattice energies and other stuff. So for the 3+ cations, we barely need any hydroxide, and those precipitate right out. The 2+ cations, we need a little bit more. So the 2+ cations, you can either use 1 or 2 to precipitate out. And then there's some cations which we really need number 1 to get to precipitate out. But these are different strengths. 1 and 2 catches most. Not all. 3 only catches the 3+. Does that make sense? And so otherwise we're going to, rather than precipitating out the iron, aluminum, and chromium, we precipitate out everything except the group, except the 1+ cations that are remaining. Silver would have precipitated out and formed silver hydroxide. But we don't have any silver at this point. And so, what we do is, this is wrong because we're doing, what are we doing? We're doing the observation. Sorry, this is going to be unknown plus ammonia, ammonium. Now, iron 3 hydroxide is brown or yellow. Chromium is kind of a green. Aluminum is white. So you're going to get a mix of colors. So you look carefully for the color here. This should result in kind of a brown, yellow-brown precipitate. But there could be some white precipitate and some green precipitate masking this precipitate, so it's hard to see the color sometimes, right? And so what is the precipitate? Well, the equation is going to be iron 3 plus 3 ammonia plus 3 H2O liquids is going to produce iron 3 hydroxide solid plus 3 ammoniums. And the ammoniums are going to be in this equilibrium here. This is the equilibrium situation, but primarily the ammoniums prevent the other ones from precipitating. And so this is the overall reaction. Yeah, you have a little bit of product. That's going to, having a little bit of product means we're going to lose a little bit of iron 3 hydroxide, but it's not a big deal. All right, once we separate that, then what? These are highly insoluble, so you don't really have to add a huge excess to get rid of these. These separate out, should separate out nicely. What's the next step in the procedure for this? What is it? Yeah, we always do the centrifuge, separate, wash. That happens all the time. This is just standard procedure. Centrifuge. Make sure you have complete precipitation. Once you get complete precipitation, centrifuge, wash.
You have to remove the other 3 plus cations from the iron hydroxide.
How do we do that?
Hydrogen peroxide.
With hydrogen peroxide and what else? So 3, we're going to take our precipitate from 2 and then add hydrogen peroxide to that.
Also use more hydroxide to get rid of the
Okay, so first we add the hydrogen peroxide or first we add the hydroxide?
First we have the hydroxide.
First we add the hydroxide?
Yeah.
So first we add the hydroxide. And the iron should undergo no reaction. And so the iron should stay. So we have FeOH3 solid plus additional hydroxide, we get Nr. Why are we doing it? Because this is important, because this is how we get rid of the aluminum. But the iron stays. And so we need to write that the iron doesn't react, otherwise you don't know what's going to happen. And then what do we do? Do we add the hydrogen peroxide after this? Yeah, this is when I say you guys need to prep your notebook, it's really important that you prep your notebook, because if you go through this just using the procedure as written in the lab manual, it takes too long. You're not going to be quick. And so what's the next step?
Add hydrogen peroxide to precipitate to make the chromium oxalate complex.
Well, is there oxalate? Did we add oxalate yet?
No, it's chromium oxide. It's going to be the product of the chromium hydroxide and hydrogen peroxide.
Well, what does it do to the iron?
It shouldn't do anything.
Okay, so what we do is we'll take the precipitate from 3 and then add hydrogen peroxide. We get Nr. And that is, it's already maxed out. Then what? We're just following along iron's path right now. Just go to the flow chart. Let's skip the procedure. Go to the flow chart. Tell me what happens next in the flow chart.
You add hydrochloric acid.
We add hydrochloric acid. So we take precipitate 4 and then add hydrochloric acid, and precipitate should dissolve. So the iron 3 hydroxide solid plus 3H plus, we'll just do it in net ionic form. There's this Fe3 plus 3 bonds. Okay, then what?
We add a potassium cyanoferrate.
Say the proper name for that. Or anybody, say the proper name for that.
Potassium hexacyanoferrate.
Potassium hexacyanoferrate. What's the charge on iron? 2. So if it was 2, it would be K4 FeCN6. Is that right? Okay. Is that solution or solid or what? Okay. And this gives us what color precipitate?
Prussian blue.
Prussian blue. In fact, this is Prussian blue. And so what is the precipitate? Well, it's iron 3. And this is, what kind of reaction is this? Loss. Somebody tell me what kind of reaction this is. Metathesis, good. The metathesis reaction. We're going to form Prussian blue. Prussian blue, it should be the positive ultimate goal for this. Okay. And so we just follow the ions in each step of the flow chart. All right, any questions? I'm going to stop here. We'll continue this next time.